So basically what we are finding is that when we put you a lens in front of the eye so that you have to focus, as when you are reading or looking at something a very, very short distance, what we are saying is that your pupil constricts very strongly, and when you constrict the pupil, the amount of light that is entering the eye is also reduced. And what we see is that this constriction, this reduction of pupil size, increases over time. So your pupil is larger when you start reading, for example, that after 20 minutes of reading. And then this constriction becomes very pronounced when you have myopia, nearsightedness. So when you have this condition that nowadays is called visual disease because it has serious consequences beyond just not being able to focus at far distances. And when you have myopia, nearsightedness, this constriction becomes stronger. So we use this and together with our previous work to support a new mechanism of how myopia originates. And the idea is very simple. Myopia is caused by an increase in the length of the eye, so that it becomes too long that it can no longer focus its images properly. And this eye growth, we think it's happening when the retina, when the tissue, neural tissue at the back of the eye is not properly stimulated. And this happens when you are spending long hours, long periods of time under low light, just not getting enough light to your eye. Yeah, so there are these two main pathways that start in the retina, really at the very first synapse of the visual pathway. You split the signal in two uh, channels of information. One that responds when there is an increase in light. This way is called light on, the on pathway. And the others when there is a reduction in light, that is light off, the off pathway. And these pathways are very, very well preserved through evolution. Every animal that forms an image in the retina, in the eye, from a fly to a human, needs on and off pathways. And what we are seeing, in this is part of other studies, is that the on pathway becomes weaker in myopia. And we know that the on pathway is not only important for seeing light and seeing images, but also plays an important motor role in our visual system. It's the main pathway constricting the pupil to light, and it's also involved in other things like stabilizing the image when, for example, you're moving your head around. But we're particularly interested in this pupil constriction. And what we find is that the pupil can be constricted because of two main reasons, multiple reasons, but there are two main reasons that are relevant for the work we are talking about. One is what we call the light reflex. So the pupil just constrict to reduce the amount of light that enters in your eye. If you are outdoors and it's a very bright day, your pupil constricts just to protect your eye from light damage. And we think that that's a good thing because, when you have a lot of light in your eye, your retina is going to be very strongly stimulated. But there is the other reflex, that is the one that we have been studying in our paper, that receives many different names. But I think for a general audience, a near reflex is a good word to remember. So it's a pupil constriction that the pupil becomes smaller, not when there is a lot of light, but when you are focusing something that is very, very close, like when reading, for example, from a phone at a 30 centimeter distance. And this is important because these two things don't have the same priority and don't work together. So the light reflex is just simply light. There is a lot of light, I get small. There is very little light, my pupil gets very big. But the near reflex could care less about light. The near reflex is just, I want to maximize the visual sharpness. And then if you are reading from something very close, even if the amount of light is very low, I'm going to constrict the pupil just to give you sharpness of and visual acuity. And we think that that's the problem because, it's going to stimulate your retina poorly because there is not enough light. And the on and off pathways, there is one thing that is very interesting to us, and is that the on pathway always have the highest sensitivity. So, for example, our retina sees better faint clouds in a bright sky. This could be a stimulus that is brighter than the background. And then, for example, a very dark shade in a gray background, for example. So the sensitivity is better for the on than the off. But for pupil constriction, this is a little bit of a technical thing. For pupil constriction, the off pathway actually is more sensitive. So this means that when you are reading dark text in a wet background, like in a book, your pupil is going to constrict more with the dark text than if you had inverted text. So that's a little bit about, there are lots of things that we study about on and off pathways, but this probably would be the most interesting one for a broad audience. Is just the fact that dark text actually will cause a low contrast, more pupil constriction than white text. Yeah, so if we have two papers that one the one that we just published yesterday and another previous one that look at the pupil, and what we are finding, and in this new one, in some way, we put the two things together. What we are finding is that myopes have a deficit in pupil constriction to light. They constrict less the pupil to light, and they are slower at constricting. So this is a problem because if we are, correct, and really what is driving myopia is poor light entering the eye, a deficit in light stimulation. If you are a myope and you go outdoors and where you could be exposed to bright light, because your pupil doesn't constrict enough to light, you're going to avoid, the brightest part of the scene. For example, looking at the sky, that could be up to 15,000 candles per square meter, or, so you maybe will look down and avoid the benefit of bright light outdoors. On the other hand, when you are indoors, because what we are finding is that the pupil constriction to near is potentiated in myopes. So you get also the worst of both worlds, because now when you are under low light, if you are myope, you're going to constrict, reduce the very little light that you have available to get inside the eye. So these would be the two things. Deficit in pupil light reflex. So I'm going to avoid bright lights because they are not comfortable. And then on the other hand, strong pupil near reflex. So when I'm under low light, I'm going to constrict it more than if I didn't have myopia. So for the clinicians, I think that is, what we are saying in the press release is just the advice that they have been giving you for many years is still a great advice. I think it should be more broadly, the message should be more broadly spread, and it should be going more and more to a larger audience, because I think that all these advices are good. And what we are giving you is in some way scientific demonstration that some of these advices are based on something real, that is pupil constriction. Just to give a few general ones: outdoors, spend time outdoors, because you're going to get bright light much more, sometimes 10 to 100 times brighter than when you're getting indoors. So these are going to give you more stronger retinal stimulation. And when you are indoors, avoid low light. So if you can read, for example, near a window, it's better than with artificial light, because the window not only will give you brighter light. For example, the light reflected from my laptop now, if I have windows, is going to be 10 times stronger than if I'm just in a dark room. But also the spectrum of light is different. For example, if my laptop has a lot of blue light, and I like to talk about blue light, we don't say this in the paper, but this blue light is kind of interesting, because the blue light is the worst at activating the human retina. We have less blue sensors than red and green sensors. We don't have blue sensors actually in the center of the retina. So very few sensors responding to blue light, but it's the most effective light at constricting your pupil. Probably for good reason. It has a short wavelength and probably is more damaging. And then, we adapted to avoid this light entering, too much of this light entering the retina. So spend time outdoors, natural light whenever possible, indoors. Reading distance, very important. So if you get things very close, the near reflex becomes stronger, you make the problem bigger. And then taking breaks. This is another advice that eye doctors usually provide, and it's a good advice, and we are seeing why. What we are seeing is that with time, the pupil constriction becomes stronger and stronger, and so if you take a break, then you will recover from this temporal potentiation of the reduction in light that you're getting through the pupil. Well, we are still, the community is discussing about I mean, we all agree if you go outdoors, you have a protective effect. If you are under very low light, you have an increased risk effect. The question is why. And we are, and you name it. I mean, hyperopic defocus light, violet light, red light. I mean, that a far distance, spatial frequency is a lot of explanations. Our mechanism, what we like about our mechanism is that it would explain why all this large variety of treatments or approaches to myopia control work. Let's start with atropine, for example. Atropine has been used for a long time, it's still being evaluated. Some of my colleagues think that the atropine works because it gets inside the eye, travels all the way to the retina, and it interacts with some circuits there that we don't know. Our mechanism will tell you that, well, it works because it blocks the muscles that close the pupil. So the pupil gets larger, you get more light, and this is why you prevent myopia progression with atropine drops. Hyperopic defocus. What we are seeing, and this, we are doing more experiments on this, and I'm convinced, okay, that what glass lenses are doing is that they are opening your pupil. So basically, the accommodation, and now introduce another term, but is the optical power of your eye is reduced, and there are three things that are coupled all the time when we look at near. Our eyes turn, the optical power increases, and the pupil constricts. So if you reduce the optical power by putting anything that is positive, it could be, multifocal lenses, or it could be positive defocus. What you are going to do is that you increase the pupil size, and then you're going to get bigger retinal illumination. There are other methods there that are called diffusion optics, that what they do is they reduce the contrast. They put these lenses so that you get less contrast. And what we are showing very clearly in our paper is that pupil constriction increases with contrast. The higher the contrast, the more pupil constriction you get. So this process, this approach to myopia control could work also by opening the pupil. And finally, outdoors activity, is just, you don't need, you are going to have a very small pupil, but you're having a small pupil because the pupil is protecting you from so much light that is there. So there is not a problem with retinal illumination. And on top of that, we know that the pupil opens up when you are moving around, when you are active, when you are alert. So that would increase even more to improve your retinal illumination.